session. There are going to be 3 talks in this session. We will start out with Sergio Busio from Minnesota. He will talk about Fourier flow of the dense gas in curvilinear geometry.
Thank you for the introduction. Hello, everybody. So I'll be playing today with the hard spheres, basically, and looking at the different collision integral, the Enskog collision integral, and how we can implement that in a lattice Boltzmann or a finite difference lattice Boltzmann, and then look at some curvilinear geometries like cylindrical or spherical. So just to have a quick picture, so we start looking from the evolution equation of the one particle distribution function. The right hand side will be or will involve the two particle distribution functions, and then as Boltzmann did with his molecular chaos ansatz, Enskog took the same approach and then said that the short range correlations, so basically the two particle distribution function, you can write it as a product of two one particle distribution function, but then you also have another factor which comes from the fact that you play with hard spheres, or so your particles are not point particles, they have some spatial extent. So this basically says, this chi, that the collision frequency will increase in your fluid or in your gas because of the volume exclusions. So your collisions are not local anymore. So we want to see how we can deal with that. So in order to treat this factor, this chi, there are two approaches. One is the standard Enskog theorem, where you take the value of the density at the contact point, or the value of the pair correlation function in a fluid with uniform equilibrium. And here I just choose one of equation of state, the Karn-Hahn-Starling equation of state. It should have been a reference, but sorry. And this will be the values. And throughout the paper, I'll use this so-called reduced density, this eta, which is given in the first equation there. Sorry, not the first, in the first blue square. And so we look at this reduced density to give us an idea of how dense our gas is from this point of view of how agglomerated are our hard spheres. And the other way is to use this Fischer-Mattfessel approximation, in which I take the density in a fluid in non-uniform equilibrium, and I do that by doing a spherical average at the contact point between two hard spheres. And yeah, these are the formulas basically. So how the collision integral looks like. So it's basically as Boltzmann. So I have the two distribution functions, two one particle distribution function, and these chi factors. So in order to use that, it's very complicated. In order to use that, I could do a Taylor expansion and collect the first terms. So the first term will be the usual Boltzmann term, Boltzmann collision integral. And then the second term will have this shape, as in the second equation, which is quite nicely. But the first one we know how to treat, and since I also want to have the Prandtl number of the hard sphere, I'll use this Shakov relaxation time approximation, which I have this free parameter, the Prandtl number, which is the ratio between the viscosity and thermal conductivity. And so this is how I'll treat the J0, so the Boltzmann collision integral. And then for the second term, the more complicated one, this one, J1, I have to do a further approximation and say all my distribution functions are local Maxwellians. So I could do some calculations, and then I end up with equation 7. So this will be the approximation of the total Enskog collision integral. So this involves only gradients of macroscopic quantities. So it's quite simple. So the equation that I want to solve is basically equation 8, in which I have the relaxation time approximation plus correction term for Enskog, for this J1. So what we want to see with this curvilinear, or where we want to get. So to go back, look at the Cartesian geometry. What happens with these hard spheres is if they get close to a boundary, in this case diffuse boundary, they will not find the collision partners, basically. So they will go around, and then as they get close to the boundary, there's not enough space for another particle to be there. So they basically free stream towards the boundary. So that means that since they will collide with the rest of the particles, they will be pushed towards the wall, basically. Since they don't have they have no collision partner there. So the density, basically, this distribution will look like this. So here we have three cases with small density, where there's not much of an effect. But as the density, in this case, the eta, the reduced density increases, I have this increase of density near the wall, is because the particles are agglomerated there. So the question was what happens when you have curved geometries? So basically, if I have a curved geometry, I have more space for the other particles to fill up the space. I have more collision partners, so this effect should be diminished by a curved geometry, or a curved geometry boundary. Sorry. And throughout the paper, just because I used two denominations here. So PM stands for particle method, which is a DSMC-like particle method in which you do these non-local collisions. It was developed by Fresotti. And the FDLB is the finite difference lattice-Boltzmann finite difference from the fact that we use off-lattice velocity sets. And this we use to solve. So then to do curved geometries, we just start from a general coordinate transformation. And this is the line element and my metric. And then equation 9 is basically how the equation changes, just like in the Boltzmann case. But what we want to do is to introduce tetrads, like in general relativity, because we want the inner product, the p squared, to be metric independent or decoupled from the metric, such that we can have we all have a metric dependence of the equilibrium distribution function. So now the equation, how it changes, becomes like equation 19, in which I basically get some more inertial forces with these connection coefficients, this large gamma, which are inertial forces that say that the particle which moves in a straight line in a Cartesian geometry will continue to move in a straight line even if you change the coordinates. So my collision integral will simplify just like before with J0 and J1, and have all these covariant derivatives. So basically what happens, so I go from Cartesian decomposition in a cylindrical cylindrical setup. I go from Cartesian decomposition to the cylindrical decomposition. Everything is symmetric with respect to, or I use the cylindrical coordinates, and I can exploit the symmetries of the flow. So my macroscopic quantities are just the integrals over the particle distribution function, as in equation 13. My macroscopic fluid equation evolutions are equation 14, where I introduce the material derivative, and the heat flux and stress tests are given below. And for my viscosity, we'll use the viscosity and thermal conductivity from the Enskog theory, which have been evaluated. So we'll just plug them in our machine. So these are basically the formulas. As if you go, so also for the Prandtl number. So for all of this, if you go with sigma to 0, so go back to the Boltzmann limit, so no spatial extent or diameter of 0, you'll recover the usual 2/3 Prandtl number for hard sphere. And so our relaxation time is given basically by viscosity over ideal gas pressure. And this is basically what we plug into our equation. And the Knudsen number is given in equation 21. One thing that we'll look at is this confinement ratio, which is a new parameter that appears, which is the ratio between the length of the system, or characteristic length, with respect to the radius of our hard spheres, or of our particles. So quite quick, in cylindrical coordinates, this is how how the equation looks like that we want to solve. The inertial forces are basically the ones that appear, and this is in spherical coordinates. But yeah, let's look. This is like the picture of what we look at. So basically, this is the spherical diameters, the sigmas, and this is in cylindrical coordinates. So I want to look at how the density varies between two coaxial cylinders. So these are some of the results. So if I put the left cylinder of radius 1, so RL will stand for radius of the inner cylinder, the left cylinder, and we'll look at the reduced radius, so the distance between the two cylinders. So what we can see is that as I move the inner cylinder, or I decrease the curvature, I'll get to a more symmetric, which is the case in Cartesian. I get to a more symmetric profile of the density between the two cylinders, and on the right between the two spheres. And then this is the comparison for the same parameters for cylindrical geometry and spherical geometry. And what we can also observe is that the finite difference lattice Boltzmann recovers quite well the particle method results. And then we look at the Fourier flow. So the first will be the cylindrical Fourier flow, in which we test for three different initial densities. And we compare the two methods, and we get quite nice results, both for density and temperature distribution between the cylinders. Then we fix the density to the highest one, and we vary the inner radius to see how the results change with curvature. And next, we change, so we fix the inner radius at 1, eta to the highest level, density to the highest level, and then we change the confinement ratio. So how confined is my fluid? So basically, what happens here is because I look at this reduced radius, I'll have that boundary effect more squeezed, basically. But still, we have quite a good agreement between the two methods. Next, we looked at the spherical coordinates. Results more or less the same. The bumps are a little bit different, but still we observe quite good agreement between the finite difference lattice Boltzmann and the particle method. And again, we did the same. We fix one of the parameters and vary the other ones, and compare the two. Here we varied the inner sphere radius, and then we vary the confinement ratio, basically. And we get reasonable agreement between the particle method and the finite difference lattice Boltzmann. And also in the Fourier case, we compare the two geometries, so cylindrical and spherical, for the same parameters. So this is for small confinement, so C equal to 4, and the highest density that we had, and we get quite a good agreement. And this is for C equal 10, so less confinement in our space. And then the last thing that one sees is the heat flux between the cylinders and spheres. And here what we did, in order to compare to Cartesian cases, we fixed the distance between the cylinders and spheres and just moved basically the both radiuses to higher values. So then that, in a sense, so as I go to very high radius, I should recover the Cartesian case Fourier flow. So the same values. So basically the first is using a very small density. And we see as I increase the left radius and keep the distance from the right cylinder or sphere, I just converge basically towards the Cartesian case, and the same for the higher densities of my fluid. So as a conclusion, this simplified Dense-Cook collision integral has been successfully implemented in the finite difference lattice Boltzmann framework, and it shows quite good or reasonable agreement with the particle method, which solves the full Dense-Cook collision integral. And this is the funding. Thank you for your attention. Yeah.
the question. So what would you say in this project was the most difficult part to obtain these results?
So basically, part of this, like the part of tetrads, was already done, like for Boltzmann. So most of this stuff. So the first line was already done. So I just had to add the part of the simplified N-scope collision integral. And then what was quite annoying actually was you had to do this spherical average around the contact point. And that meant to have a spherical average between cylindrical slices or spherical caps, and to do that two sphere intersections or cylindrical spherical intersection in each point with very good accuracy. And the problem is that there's no analytic formula between intersection of a cylinder with a sphere, which is like, I was very surprised. So I had to implement some packages for that, but yeah, it works quite nice. Yeah, it works quite nice. I think the most annoying part of this is that where we should get proper speed up. I don't know exactly which one. Let's say this. So at small densities, basically you go to ballistic regime. If you have a very small, but then for lattice Boltzmann or for like DVM methods, you need to increase the quadrature number. So you need very large velocity sets. So it's a no-go. But then if you go, so where you need a very small velocity set, so for large densities, small Knudsen, then your approximation is no good enough. So basically you're cut from two sides. So where you should really beat particle method in efficiency and time, you lose more and more accuracy, which is, yeah, quite annoying. Yes. Good.
Victor. Yep, that's me. Yeah, when the computer went into Windows update today. That's the. Can I plug it in, or is that like that's the controller for the? Ah. Let's see. Yep. Good. Thank you very much. So indeed, we're talking about lubrication right now, which I find is a perfect timing as concerning the plenary talk earlier. So what I'm going to present you is our method model to develop or to model those lubrication scenarios that we have developed in Erlangen at the Helmholtz Institute together with a lot of people. Yeah. So wetting lubrication, what we're talking about is basically droplets or liquid films. So you've got examples of droplets on a windshield or a maple leaf. You've got like technical examples where, for example, inkjet printing is a thing, or all kinds of coating techniques. It's also important in a lot of biological scenarios. Here I show in green that's cell membranes, and the purple things that's protein-rich liquids wetting the cell membranes, or over here you see a picture of an oil film on a puddle, just to give you a few examples of what to keep in mind when talking about wetting. So let's talk about the model. So what we want to describe in the simplest case is a solid support, let's say a table, then you have like water on top, let's say you spilled some coffee. We describe this, or let's say the easiest way or the most straightforward way to describe this is just Navier-Stokes equation. And of course you have to do a multi-phase thing. So there's such that you have a vapor phase, you have to do some handling of the solid boundary. But you can simplify this by considering the film as described by its height field, and by assuming that this height is rather small as compared to typical length scales, which applies to a lot of scenarios, to a lot of liquid films or droplets. And then what you can do is you take your Navier-Stokes equation, you integrate from the point, let's call it 0, to the point h. Then what you get is a different equation that's called the thin sheet equation, or also sometimes called the lubrication equation. And then when we're also interested in microfluidics, we're typically in the Stokes regime. So if we then apply the Stokes regime, we get what is called the thin film equation. And that's this one I've written down for you. So it's a conservation equation of the film height h. It depends on, it's driven by the pressure gradient and by the surface tension gradient. And in the Stokes regime and lubrication approximation, it's able to describe the behavior of liquid films quite well, as has been proven throughout literature. So our ansatz to model this is actually we do not solve really thin film equation, but we solve the thin sheet lubrication approximation, the lubrication equation, by a lattice-Boltzmann scheme that I'm showing to you in a second. So this is our lubrication scheme. It's in many parts very standard, so we use a D1Q3 or a D2Q9. We don't need to go to a D3Q whatever, because as we're looking at just the film height, we don't care about the third dimension. A liquid film in that sense can be described in only 2 dimensions by its height field. So we do a standard BGK. That is, we equilibrate our populations towards some equilibrium with a relaxation time tau. Then we calculate the moments. That is, we sum all our population, and we don't get the density as you would typically expect, but we get the film height h. And if we sum up the lattice factors times the populations, we get this film height h times height flux u. So that's the first difference. And the second difference towards a standard lubrication, standard fluid dynamic lattice-Boltzmann is the equilibrium function. It's almost the same. The only difference is we do not use this one here. So we cancel one term from the equilibrium distribution. And that leads to the fact that what we're solving is not standard Navier-Stokes, but we do not have the dissipative term. So the viscosity times second derivative of velocity, that's not there. So as you see, that's if you replace h by a rho in your head by density and big U by velocity, then you have almost Navier-Stokes equation, but no dissipative term. Then the final step is we're applying some forcing. So we choose a force and we choose it like this. So we have a pressure part, we have a part that comes from the surface tension gradient, and we have this last part that is basically a friction force. So that's how we re-enter dissipation into a model. And then plugging in this force into the equation that we solve to second order by our scheme, we solve the thin sheet equation over here. And with this, we can model lubrication. We can model the evolution of the film height h, and actually a bit more. We also have information about the flux u. And that's how we can solve our lubrication problem, how we can model a liquid film or a droplet. So let me just show you a few examples. The first thing we can do is we can look at thin film dewetting. So the idea is you have your solid substrate, you have a very thin liquid film, let's say 10 nanometers, and surface tension are chosen in such a way that it's preferable for the film to form droplets and not stay closed. And then if you run the simulation or also a corresponding experiment, what you see is the film breaks into droplets, as you can see here. So the difference between those two simulations is that for the left side, I chose a no-slip condition between the liquid film and the solid boundary underneath. And on the right-hand side, I chose there to be a certain slip. And the clear difference is that for the no-slip, you see those satellite droplets emerging upon film rupture that you don't have in the slip case. There, everything is way more homogeneous. And that is actually in line with experiments. So here you can see the black things, that's droplets from, it's a polystyrene film dewetting on different substrates. Here you can see those satellite droplets, and here you don't have them, which is also associated to slip. So we can kind of reproduce it, even though not fully. The size of the features are a bit different, but the qualitative behavior is there. Another example is liquid droplet coalescence. So you put two droplets next to each other. What will happen is they merge into a single drop due to capillary forces. You can see a video of a simulation right here, two droplets becoming one. So what is typically studied in the context of coalescence is the height of the liquid bridge here, so this HB, and the width of this liquid bridge. So we measure that within our simulation. We plot it against time. It's a log-log plot. You can see here, you can see that the bridge height grows with a power law of time to the power 0.8 something. And the bridge you can see grow with a power law time to the power 1/2. And that is pretty much in line with what is also reported in literature. So also nice. Then we went for more complex scenarios because so far we just had like simple films on solid substrates. Now let's look at a liquid film that might have a product that is blue, a reactant is blue, a product dissolved that is yellow, and then we have those purple particles that are catalyst and turning the reactant into product. And on top of that, we want to model a possible distribution of catalyst. So it might be, let's say, buoyant, might be homogeneous, or it might sink to the substrate. So we model that with a thin film equation coupled with an advection diffusion equation. We model surface tension to be linearly dependent on the concentration of product and reactant. And yeah, that's pretty much it. And we have this control parameter alpha that tells us about the buoyancy or the distribution of our catalyst. And that's a model we initially developed for the application of so-called supported liquid phase catalysts. So the idea, you've got different examples from literature. So let's talk about this one. The idea is you have a liquid film. Inside the liquid film, you have a catalyst dissolved, then reactant comes, enters the film, reacts, product leaves, goes away. And the good thing about this, you have all the benefits of homogeneous catalysis, but you're not transport limited. As in the gas phase up here, diffusive transport is way faster than in the liquid phase here. So that's the basic idea. Essential for this kind of catalytic systems is that the liquid film stays closed, that it doesn't break. And we've seen just a couple slides earlier that liquid films actually tend to do that. They break into droplets. So to study the stability of those films, we set up some simulations. I will show you two exemplarily. First one, we have alpha 0, so meaning catalyst is homogeneous as shown here. Then you have this blue thing, that's the liquid film, and you have 3 lines. They're going to be purple for the catalyst, yellow for the reactant, and blue for the product. So running the first simulation, you see that in this case, the film is pretty stable. So we started with some noise and all that noise dies away, becoming a flat film. Then the second example I have for you is alpha positive, so catalyst sinking to the solid substrate. And here something interesting happens. So we have the formation of instability. We have this clustering of catalysts, those purple spikes. And then finally, we have the formation of droplets. So when we first saw those spikes, we were quite, well, intrigued by that. And we wanted to understand where do they come from. And we found the answer when looking at the flow field. So driven by the surface tension gradient, there's a shear stress at the surface and the typical Laplace pressure within the film, you get this kind of circular flow fields that are, that accumulate the catalyst and lead to those purple spikes. So the next model I want to show you is for multiple layer of liquid films. So the idea is we have a solid substrate here, then we have a first layer, let's say mercury, then we have a second layer, let's say water, then oil, and you may stack as many as you want. They're immiscible in this model. There's papers showing up to 8 pairwise immiscible fluids, so it's possible to have many of them. So we model them by their heights again. And well, this we did with having in mind applications like liquid lenses, liquids on liquids, or wet on wet printing or coating processes. So we write down the thin film equation, the thin sheet equation for this n-layer system, and then we implement it. And I'm going to show you again a few examples of simulation that we did. First thing, film stability. So here you have a thick, let's say, water film with a thin oil film on top. And if I run the simulation, it breaks into droplets, forming this kind of droplets you see here. Here you have an example of a 2-dimensional simulation of 3 equally sized liquid layers. The difference between the simulations is the individual surface tensions we chose. And again, you can see both films breaking after a while, but they do so in different manners, forming different kind of configurations after film rupture. On the right here, I show you all the possible combination that can come out of the simulation of 2 liquid layers. You can imagine that for 3 layers, it becomes even more complicated. There's even more possible configurations. So to further test our model, we had a look at contact angles. So as you might know, for a liquid lens, as you can see here, the expected contact angle can be calculated from the given surface tensions by the so-called Neumann's law, or for the Sessel droplet, it's Young's law. So we do is we initialize one droplet with a too large initial contact angle, one exactly right, one that is a bit too small, and then we run the simulation. We can see that they relax to the expected shape. So we do so here on this axis, you have the expected angle by Young's or Neumann's law. On the y-axis, you have what we measure, and you see there's a good agreement. And when we approach 45 degrees, where the lubrication approximation breaks, it slightly worsens. In terms of percent, we have at worst an error of 12%, typically better. So for a lubrication model, that's quite good. Yeah, on top of that, there's many other models where I don't want to go into so much details. For example, we could do liquid films on pattern substrate. The red one is supposed to have a different surface energy than the yellow. We can do liquid films on curved substrate, as shown in this simulation. We can do liquid films consisting of, let's say, a blue and a yellow liquid. The difference between the 2 simulations is that here there's a higher difference in surface tension than here. And if we run the simulation, those do not coalesce, whereas there do. We can do liquid films inside of a pore geometry, or we could do liquid films with a monolayer of surfactants on top. So with that, I'd like to conclude my talk. So the message basically I wanted to convey is that within this framework, within this method, we can do a lot of things. We can do simple liquid films. We can add all kinds of solutes, of chemical reactions. We can do it on heterogeneous substrate. We can do multi-layer thin films. We can do miscible liquids. If you want to check out our work, parts of it is to be found on GitHub, and we also got at least a few papers out of it. So this is the original method paper. This one is about reactive film, and the multi-layer thin film that should be published on arXiv like any day now. Thank you very much. Yeah, please. Mm-hmm. We don't really have problems with the stability concerning velocities in the bulk. What we do see, can I run my videos? Or what we do see is for 2 layers, it's typically very stable, at least for everything I tried. For the 3-layer films, we somehow see, so in this video we don't see, but if the surface tensions are chosen too large numerically, we see problems in regions here where you have multiple of those. It's kind of, this is supposed to be a de-wetted film, so we keep this small precursor layer, which is what in thin film equation typically is done. And we get numerical problems sometimes in those regions where we have multiple of those precursor layers on top of each other. But in the bulk, I haven't seen. The velocities are basically like shown here. So we start at the substrate with a no-slip or slip boundary, and then they start to build up. So you have a smaller velocity in the lowest layer than you have in higher layers. So we never tested more than 3, and for 3, we don't really get problems with too high velocities so far. In vertical direction, none at all. We're describing it by a height field. Is that what you're meaning? How large the resolution is in this direction? Where we're not resolving this direction. The whole idea is to describe liquid films by their height or thickness, and therefore the only discretization we have in this direction, and in this direction it's continuous. So we have a float value of film height in that position.
surfaces also. So you have like different profiles for the curved surfaces also together.
You mean for this thing? So in principle, we did the things singly. So we have this one on the flat, and we also can do the curved surface or also the pore. So the application we have in mind is this kind of system where you have those porous structures that are covered in a liquid film containing the catalyst. And therefore, you definitely need this kind of curved surfaces. So that's what our plan, our next step to do is to do exactly this. So we want to do basically this pore combined with the reactive film. That's our plan. We've got a master student working on it, but so far we're still testing if that. So we have the code implemented, combining this with the reactive film, but right now we're testing if it even does what it's supposed to. We don't have results so far.
Yes, sure.
Do I need the microphone?
Yes, like on the recording. Yes.
Ah, then yes.
Is it on?
Has to go like this, huh? I suppose. Huh? Wait, we don't go for below here.
So, I think so. As long as it's close to it, I think it's
Is it the one?
opposite.
Opposite direction.
That's
Like
bad,
this.
Yeah,
Then.
exactly.
Okay.
Push comes to shove, we could keep
Yeah.
just a bit.
It's good.
There you go.
And then this goes here. So welcome everybody. There are many places you can.
No, it's- Oh, it's I said before, this is like the problem. Really, you will be talking about substrate friction implementation, multi-particle collision dynamics, emerging damping dynamics, theory, turbulent pilot active system.
That was a long title. Thank you very much for the introduction. So I will split the title in pieces, and I will start to say what do I mean by chiral active matter. So chiral, you know, are particles with a certain symmetry that are not able to superimpose. But what we mean is particles that might be cylindrically or spherically symmetric, but that due to their motion, typically rotation, they become dynamically chiral. So they are able, they have a well-defined direction of rotation. There are many examples in nature. For example, bacteria or sperm with flagellae, which are constantly rotating. Smaller scales, proteins in a membrane, which are rotating, or these nice volvox algae, which are rotating, forming these colonies. So there are also examples of synthetic systems like these so-called quink colloids that are colloids with a certain dielectric asymmetry in them. When they are inside an electric field, they spontaneously start to rotate. Spontaneously means also that they don't have a well-defined, but you have some of them that are left, right-handed. But what we are going to speak today is about other type of colloids that are were the topic, so that were synthesized by Dirk and Yongxian in Oxford and then in China. And these are rod-like colloids that have attached in one of their extremes, as you can see here, a magnetic particle. And this magnetic particle has a momentum which is perpendicular to the main axis of the rod. So they put these micrometer particles, micrometer-sized particles, in a substrate, and they put these systems of of magnets, and they are able to apply a rotating magnetic field. And what happens is that you have the rod and it starts to follow the field. And if the frequency is small, it's just following, but there is a regime of frequencies in which these colloids precede and they stand, and they are like cylinders which are rotating perpendicular to the surface. And they, as you will see, form nice structures, but let's start. So they form this vertical orientation, and they are all co-rotating in the same direction and at the same time. So yeah, we are interested in making simulations about these systems. And then Joshua Mega started 4 years ago, now he's a postdoc, and did these fantastic simulations. And the idea was that since these are cylinders, and the important thing is that they carry the fluid around with it, but the main dynamics is occurring in 2 dimensions. So we are, again, working in 2 dimensions, and we have this colloid with a solvent around. And what happens is, in principle, if you have only one of these particles, it's rotating, but it performs Brownian motion, so it's not really displacing, because what the magnetic field does is to make it rotate. But if you have another particle close to it, what happens is that it drags it with it. And here you can see the experiments of 2 particles, how they are rotating one around each other. And if we make simulations, you also see this type of rotation, which is going to be faster or slower depending on how far away these particles are. And of course, there are thermal fluctuations such that they will displace close or far away. And okay, we don't do lattice Boltzmann. And since the community I know is basically lattice Boltzmann, this is a transparency that I used very long ago. So many of you have seen it. And it's just to give you the main idea in multi-particle collision dynamics, which is a little bit younger than lattice Boltzmann, but already not so young anymore, from the previous century, actually. So the idea is the solvent, I'm talking about the solvent, are point particles that are not, they don't have a particular size, and they displace continuously in position and in the phase space. So they have continuous positions and velocities, and they have these 2 steps in discrete increments of time. In the stream step, they don't see each other, they just stream, and in the collision, they interchange momentum only with the particles that happen to be in the same collision box. So you sort them, and they interchange momentum. There are different ways of doing this collision. My favorite one is this stochastic rotation. And here I write you the way that they interact to show you that the main idea is that you extract the velocity of the center of mass. So they only see each particle sees the velocity of the center of mass of all the others. And in principle, you rotate by an angle alpha the difference to the center of mass, and this ensures conservation of linear momentum. Here we need conservation of angular momentum. So we also calculate the angular momentum in the cell and make sure that it's conserved. This is what I will say about it. Then you can also have use all the tricks of lattice Boltzmann and molecular dynamics to put boundary conditions. And then we also put colloids on it. And here I directly show you one of the simulation boxes. It's 2-dimensional, which means that you can make it much bigger. And this code is now GPU unparallelized. And each of these points that you see is one of the colloids that it's rotating. So we remember that they were dragging the neighbors around. And if you put many of them, what happens is that vortices start to appear. So you have 2 particles, 3 particles, 10, 20, and they are vortices of all different sizes, which reminds very much turbulent-like behavior. I would like to show you, wait a second, the same movie, but no. This is what, sorry for, I prepared the talk in Mac and it doesn't want to work. No, mal. Okay. What you see, you have seen here it is. You have seen here is the vortices forming. If you analyze the vorticity field, what you see is that there are areas of large vorticity, means that the whole vortex is rotating in the same direction as the rotors. and areas of very low, which is negative vorticity, because if there are two big vortices rotating in the same direction, something needs to adapt in the middle, and then it counter-rotates. So all the rotors individually follow the field, but collectively there are some of them that need to go against it. So you have areas of large vorticity and low vorticity, and if we analyze the density of rotors, you see that they are accumulating exactly in the same areas as there is large vorticity. And this is the signature of odd viscosity. So what we see here is that this turbulence appears at the same time as, and they are indeed related, as this odd viscosity system. But the point of today was to go a little bit farther. So here we show you the one of these snapshots of the simulations where you see the vortices, and this is the same analysis done for the experimental system. You see that phenomenologically it's the same, vortices, positive, negative, and accumulation of particles in the same places. But one thing that you can see is that the vortices experimentally are clearly smaller. And it's the vorticity in the simulations gets much faster. Here is more damped and more, and they become smaller. And the question is, so we had the first paper, and then we said, but why is that the case? That's something missing in the simulations, and now it's too fast. Okay, something is missing in the simulations, but first I want to show you one of the quantities that we analyze. I will not go in all of them. I can tell you if you are interested, but one of them that it's very common in this field is this energy spectrum, which is the correlation in reciprocal space of the correlation of the velocity. So here you have the wave vector, which means that these are the smallest distances. And if you go to small wave vectors is the large vortices. So let's look first only at the blue. The blue is the results of the simulations. And different blues, the intensity of blue is the density. So if you have very low density, there are only the rotors, and then you see that there are very small, there are almost no vortices. As you increase the density, then they start to collapse, all of them, in this power law behavior. And if you increase very much the density, then they cannot move. So again, there are not large vortices formed. But you see these very large, so there are here many densities in which you see this power law behavior, which is due to self-similarity, and it was known in classical turbulence. And that was the blue, that were the simulations. But if you look at the red, that it's the experiments, but you see the experiments follow the same trend, but the spectrum is cut, clearly cut, because these large vortices are not forming. So here, in principle, we can go all the way to the system, because the vortices become as large as the system size, while the experiments are not they don't see this. So there is a dominant vortex scale, which is not given by the system size. So how to improve the simulations? And that's coming back to what are we simulating? We have these the rotors. We have one of them is on the substrate, but we are doing 2 dimensions, so 2D simulations. The things that one can think about is, are dipolar magnetic interactions important? What is the effect? Because you have hydrodynamics, you know how hydrodynamics in 2 dimensions have divergent contributions, and there is the substrate friction. These particles are on top of a substrate, and they are dissipating energy. So we can check, I will not show it today, that dipolar magnetic interactions are negligible. And then we decided to look at what was happening with the substrate friction. And in order to implement substrate friction, I told you a little bit about MPC, and the idea is to consider, we have just 2 dimensions, so we cannot put a friction with a substrate because our system is the substrate, so it is all taking that into account. But we thought if it interacts with a momentum reservoir, that it's absorbing some of the energy, that might do the work. And there is an idea which is used for other, for interaction with walls and for other things, that it's the interaction with virtual particles. Here I've put a little red particles, and the idea is that these are my MPC fluid particles, and these would be these sources, these sinks of momentum. If you remember the interaction in the collision, since all the interactions were happening in the velocity of the center of mass, now the idea is that the center of mass considers the particles that happen to be there at that particular moment. Sometimes it's more and sometimes it's less. And a few of these virtual particles. So here is, for example, in this box, there will be 0, 0. Here you have 1, here you have 2, the ones that happen to be at that time there. And this interaction is just a random number, which is Maxwell-Boltzmann distributed with average 0 and so the variance will be given by the temperature. And this number is changes from box to box, but we have a density, an average density of virtual particles that can be 1, 2, 0.1. And this is what we want to relate now with the friction. And how to calculate the friction is relatively easy because it's the momentum transferred on average in one of these collisions. So how much momentum was before and after the collision. MPC is done such that if you have no virtual particles, that's exactly 0. So conserves linear momentum locally. But since we have these virtual particles, there is a certain momentum lost. And this we can calculate and average by the and normalize, and this is a calculation that can be done, and you get that the friction is proportional to this number of friction of virtual particles that you are putting, and with the length of the collision time. And related to this, we can define a solvent damping length, which it's related to the distance that an eventual perturbation, 3 minutes, okay? That an eventual perturbation would decay. And okay, you can input this here, and you see this is the friction, is the thick line, and increases with this number of particles, and this correlation distance decreases. If you have less particles, it will take less time to damp, less distance to damp. And if you look at the numbers, if you put 1 particle on average per collision box, you are that your damping length is 1 collision box, which is far too much. So you need very few of these virtual particles. Actually, it's 1 in 10,000 or something like that. What you need in order to have that, you have a damping length over 20 boxes or something like that. And now, well, this is that we are able to measure in solvent, and this prediction works very well. And here you see what happens in the system if you put this increase in friction. This was the simulations without virtual particles. And if you increase slowly the number of virtual particles, very few of them, but you see that the vortices start to become a little bit smaller, clearly smaller, which is exactly what we were missing. And this is my last content transparency. We do, again, the energy spectra without friction. And when you put friction, you start to see that is being, you have this cutoff of the energy spectra, and this defines a typical length. So this typical length here, what we have done is to put the virtual particles to have the different friction, and we measure a length that it's related with the friction. That is, this black line is this decay length of the solvent, and this is larger because it's not the decay length of the solvent, but of the colloids. But the functional density, the functional dependence is exactly the same. And so we have this emergent damping length, which is related with the solvent. And the last plot is, can we reproduce the experimental results? So given this damping length, we can choose the friction that our experiment need, and then you get very nice. So in blue, the simulations, and in red, experiments. These are 2 different densities in the experiments, and the damping length is the same because these experiments are done in the same lab with the same rods and the same substrate, which means that you have 1 value of the friction. So, and then I'm at the end, the conclusions are also my title, because this is rotating and coming back to the same place. So we have implemented substrate friction in multiparticle collision dynamics, and I think this idea can be used in other methods. I don't know so much about lattice Boltzmann, but I don't know if something related could be done in a lattice Boltzmann system. And then we see this emerging length in a turbulent active carrier system. Acknowledgement go to all the people that have participated in this work. And I would like to thank you for your attention. And I'm very happy to be back in. Okay. Okay.
Even the experiment is 3D and 2D is for the simulation, that causing the difference rather than the friction.
It could be the same. One thing is that in 2 dimensions, you also have that the hydrodynamics are diverging. So we have a way of, so it can be that the length, the range of the hydrodynamic interactions is too long. And this is the fact of putting friction is making that the interaction, so how far my colloid is dragging other colloids decreases a little bit.
Right. The eddies start to correlate.
Start to?
Merging into ever larger size indefinite.
In simulations. In
the energy is going to smaller scales, and in 2 dimensions, the energy is going to larger scales.
Yeah, so you have the rotors that act like vortex elements, filaments.
the
They
question.
generate small scale, and then they propagate backwards into larger scale in 2-dimensional filaments.
Yes.
But in 3D, I suppose the experiment is done in 3D. It does not do that.
The particles are not moving in 3 dimensions. So the experiment, there are no experiments in 2 dimensions because 2 dimensions we are idealizing. But these rotors are moving on a substrate. They only have a 2-dimensional motion. They are not going up and down. I don't know if that, so these rotors are really moving just on a surface. The experiments are also done on a surface. Yes, I did not put any snapshot of the, but I can show you. So you see this type of picture of that I saw only the 2 of them. They are always displacing on a surface and they are moving around each other, but they are not going up and down because there are rotors that are, and if they would go up, they would not be rotating. It's like a film, yeah. So that might be why it might be a 2-dimensional motion. Alexander?
Very nice talk. I was wondering about the friction. So the friction that you put into particles, right? I'm just wondering, wouldn't it be much easier to just say each particle has a friction with the substrate and therefore the velocity is scaled by some small factor for all the particles? Would that be the same or would that be fundamentally different?
That would change all the advantages of MPC. So, as I said very quickly, if you look at the so MPC lives of applying this and of calculating the velocity of the center of mass. Now you say I have to renormalize all the velocities of the particles every time. And then I would have to put energy in because you are losing energy. But instead of that, I just add 1 in 10,000 boxes. I add 1 particle that subtracts a little bit of energy. So computationally speaking, it's almost for free. You have to do it, but it's...
Do your particles stay in the same box or do you put them in different boxes each time you do that?
The virtual ones.
Yeah, the virtual.
They are moving like the other ones. So each time you generate with a probability 1 over 10,000 if there is going to be a particle or not. So this is the probability that you get a particle. We don't count them, so it is a probability.
So they just pop up every
They
time
just
you
pop
take-
up wherever they, and because they have to be, otherwise you would have sync. Otherwise you would have a place that it's more, so, yeah.
B22 thing. I mean, in 2D spectrum erosion. So the moon they simulation in the experiment that would be still 3D directly.
That's what we were thinking. So when this is the line that we were thinking on, and the first thing that we were happy with is that we could neglect this type of interaction. And then we were thinking the flow is, I mean, in a way, it's not so bad. Even if you get disagreement, what it is, I mean, this was type of a green. We are seeing the same phenomenology. We are, and the odd viscosity, we can also compare it in the two experiments. It also has in some regime, but yeah, but it's not very nice that you have the Stock paradox and the Jeffrey paradox and blah, blah, blah. And we were thinking, I mean, we would not be able to do this. If this would be rods, we would be much, much smaller. We could, I mean, there are many simulations of MPC in 3 dimensions. There is no problem with MPC in 3 dimensions. We do ever so, but of course you cannot go to this massive, it would be big, but not so. And the fact, I think that the fact of adding the friction also makes that the hydrodynamics in 2D are not divergent. So it has like, for the same price you get two.
The red points, those are the rods, right?
Here are the rods, yes.
The way I understood, you're just modeling the rods and nothing else?
No, no, no. I mean, I cannot zoom in here, but we are modeling something that looks more like this. So actually there are 6 boxes and there are the separation, and typically it is really, you are dragging all the flow around it. I think I counted because I forget these numbers depending on the system. We have done many system sizes or so, and I thought somebody's going to ask how many particles, and I forget. But I think it goes to 100,000, 500,000 colloids and something like 30 million MPC particles, something like that. That's a big one, so that's a big darling. But simulations, smaller simulations, how many? So simulations with 1 million particles. So typically there are many solvent particles. So here you have 10 per box. That's why you have hydrodynamics. Otherwise, because we are not putting they are moving due to the solvent. The solvent is dragging the particles. So the translation is all due to solvent.
One is there a different numerical method in which you could compare your results? Because now so the friction effect comes in through the virtual particles. Is there an alternative numerical method which you compare? Someone else model that system here?
This model, I think so. It has been done, Ignacio I know, but so now suddenly I am, so who has modeled chiral particles with lattice Boltzmann? It's done? I mean, I think no, I see no fundamental problem for doing that. Yeah. Yeah. So here you apply. So that we are imposing, yes, because otherwise would not be. So we and the way of imposing this, but that could be the same in lattice Boltzmann. So we say they are rotors because of the magnetic field, but that you are dragging them.
Point vortex exchange vorticities with the lattice Boltzmann flow solver. And these are followed as point vortices.
That could be done, yeah. The question is, I mean, there are different solutions for the same problem. Is it one better, the other one, or it would be one more correct than the other one? That we don't know. I don't think large size is a problem now. I don't think we would learn more with bigger systems. So it is, yeah. But
Have you tried all the same simulations without the angular momentum conservation in the division?
no. And I think it would be more coherent. So I have another problem with another completely different system with theoretic ones, and the lack of angular momentum is makes so it is more coherent, but it's type of an artifact. But
I think we need to stop now. Oh, yeah, next session.
there is, yeah. Thank you very much for all the questions. I forgot mine. Thank you. Thank you.
Yeah. Very interesting.
Huh?
That's very interesting.
Wait. I managed to put it in and now.
Yeah, I think this was supposed to be on 15 minutes ago. Yeah, but then people kept asking questions.
No, it ended.